Hi everyone, in today's video we will be going over kinematics in 2 dimensions. So this video uses a lot of concepts such as vectors and one-dimensional kinematics that we've covered in past videos. So if you don't have a solid base of those yet, I would recommend watching those videos before diving into this one. So we know that kinematics describes motion, and so far we've only practiced kinematics in 1 dimension, where our velocity, time, and displacement acceleration were in 1 dimension. But more commonly, 2 dimensions or even 3 dimensions, kinematics is more useful. So a common subject in kinematics in 2 dimensions is projectile motion, where the motion of an object is projected into the air is subject to only the acceleration of gravity, unless a force acts on it such as air resistance. So projectile motion can be such as throwing a ball or hitting a tennis ball or just throwing anything upward onto earth and back down again. That's projectile motion. So something that we'll use a lot in 2 dimensional kinematics is vectors. So we know that vectors is a quantity that describes both direction and magnitude. Vectors in kinematics include displacement, acceleration, and velocity. What we learned in the past video is that vectors can have x and y components. So that means that vectors can happen in 2 dimensional spaces. So we learned that there's a trigonometric way of defining vectors. Let's say we have a vector named A whose magnitude is also A. We know that its angle, let's say, is theta. In order to find its x component, we will do A cosine theta. In order to find its y component, we will do A sine theta. Also, we know that tangent of theta is equal to y over x. So these are different ways that we can find x, y components if we're giving magnitude and the angle, or how we can find the angle given y and x, and also the magnitude of the vector. So, kinematics has a lot of vector components: velocity, acceleration, and displacement. And using these trigonometric identities, we can convert these equations that we know from 1 dimensional to 2 dimensional. So as you can see, this chart shows the conversion of our 1 dimensional kinematic equations into 2 dimensional kinematic equations. And what's actually really simple about this is the equations are the same for both x and y. However, they're separated into their components so that the velocity, displacement, acceleration are different and independent to each other. So components are independent to each other. That is a very important topic. So the acceleration in the y direction will not affect anything in the x direction. However, one thing that they do share is the time. Time is common between both the x and y component. So, in order to show you a better visual of 2 dimensional kinematics, I'm going to show you a graph of how projectile motion works and how we divide them into components. So, imagine we are standing right here and there is a ball. We kick it upwards with an initial diagonal velocity with some angle theta to the horizontal. So we know that when we throw a ball, as it goes up, it reaches a peak height and then it starts to drop and reach the ground. So we know that at each of these positions, our ball has a new total velocity. And the reason for that is because we have a vertical acceleration that's pointing downwards, which is our gravity. However, in our x direction, we have zero acceleration. So looking right here, if we broke up our initial velocity into our y and x components, like so, y and x, our x components would stay the same the whole time, like so. However, our y components are changing. This, as you can see, it's getting smaller until at the very peak, there is no y component because our gravity is negative. So it's taking away from the initial velocity until our y component starts becoming more and more negative. And that reason is because we start with a positive y velocity, a negative acceleration will take away from that initial velocity until it's negative. So that's a basic diagram of projectile motion. I'm going to go over two practice problems with drawings in order to further explain how we utilize these equations. Okay, so our first question is a simple projectile question. A projectile is fired with an initial speed of 110 meters per second at an angle of 36 degrees above the horizontal. So using this information, we need to determine the total time in the air, the maximum height reached by the projectile, the total horizontal distance covered by the projectile, and the velocity of the projectile 4 seconds after firing. So there's a lot going on here, and the best way to break this down is to draw a picture of the scenario and also make a chart of what we know and the variables that we don't know. So starting off, we know that we have a projectile here fired with an initial velocity of 110 meters per second and an angle above the horizontal, which is 36 degrees. Since there is no additional force stated and we know that it's on Earth, we know that the acceleration acting is in the y direction and it's gravity. So our projectile would look something like so. So some important things to know in kinematics is that the peak displacement in the y direction is where our velocity in the y direction is also zero. So that is also a significant piece of information that can help us later on. So now let's list what we know. We know that our initial velocity is 110 meters per second. Our gravity is negative 9.8 meters per second squared, and that's because in this case we're considering up as positive and down as negative. And we also know that our theta initial is 36 degrees. So something important about kinematics is that the problems they give us, A, B, C, D, aren't necessarily the order we have to go in. We have to go in a way that we can use our information given to find other information in order to find parts A, B, C, and D. And in this case, right now we don't have enough information to find the total time in the air. But we do know that at the peak height, our final velocity at this point will be zero. So that means our first step is to look at things in the y component in order to find the maximum y displacement, which is called delta y. So looking at our y direction equations, we know that there's a couple different ways that we can solve for delta y. One says delta y is equal to v initial times time plus 1/2 a t squared. That won't work since we don't have time. Another is v final squared equals to v initial squared plus 2 times acceleration times the displacement. That could work since we have all the information except for displacement. And lastly, we have v final is equal to v initial plus acceleration times time. So that one also has time, which we don't know. So it looks like the middle equation is going to be what we're going to use. And in this case, we don't know what delta y is. So our equation that we're going to use is going to be v final in the y direction is equal to v initial in the y direction squared plus 2 times our acceleration times our displacement, which is delta y. So before we put in our variables, we're going to need to isolate for what we were trying to solve, which is delta y. So in order to solve this, we'll do some algebra. Vfy squared minus viy squared divided by 2a equals our delta y. And remember, in this case, we're looking at the y component, and we know that our y component, our a is going to be g. Okay, now the issue is in finding the y component of our initial velocity. And remember that I went over the trigonometric uses in vectors, and we know that velocity is vector. We know that our v initial is 110 meters per second with an angle of 36 degrees above the horizontal, right there. So that's our vector. In order to find the y component, so v initial y, we can just do sine of 36 times 110, which is equal to, using my calculator, 110 times sine of 36, which is equal to about 64.66 meters per second. So that's our initial y component of our velocity, and we know that the final component of our velocity in the y is going to be 0 meters per second, because we know at the peak height of our projectile, our y component in velocity is going to be 0 meters per second. So now let's plug this all in. Okay, so we plugged it into our equation, and make sure to remember that our gravity is negative because we're considering the upwards direction as positive. So we're going to plug this in, and it's going to be 0 minus 64.66 squared divided by 2 times negative 9.8. And that's going to give us a delta y of 213.3 meters. Okay, so now that we've found our delta y, that's also an added piece of information into our known chart. So we know that our delta y is 213.3 meters. We have enough information to use y equals v initial times time plus 1/2 acceleration times time squared in order to find our t. However, that's a bit more difficult in order to isolate time. So I'm going to teach you guys a cool and easy trick that'll help you figure out time. So we know that right here at the very peak, we have velocity 0. And something special about the very peak is where our time is also equal to time final divided by 2. So that's also a really important piece of information that you can use as a trick later on. So if we find the time that it takes to reach Vy, which is going to be our final velocity of 0, we can find the half of the total time that it takes. So, using the equation V final equals V initial, V final y equals V initial y plus A times t, we can isolate time. And our time is going to be time final divided by 2. Or in time final, I mean the total time in the air. So isolating time, we're going to have V final y minus V initial y divided by acceleration, which in this case is g. and that's going to be t final divided by 2. So in order to isolate t final, we're going to multiply both sides by 2, which is going to cancel out the t final divided by 2 and leave us with t final. So putting this into our calculator, we know that v final is 0. Our initial is 110 times sine of 36, which is 64.65. So negative 64.65 divided by negative 9.8 times 2 is going to be our total time, which is 13.2 seconds. So now that we have added our time final into our known chart, we can easily solve for C and D. So, something really important about horizontal components in projectile motion is that horizontal does not have acceleration. And that is a really important concept that sometimes gets messed up, and people assume that there's also gravity acting in the horizontal direction. But remember, gravity is only acting in the vertical direction, and the horizontal has no acceleration unless stated in the problem or if there's a horizontal force acting on it. So this helps make finding things in the x direction a little bit easier because we don't need acceleration. So, since we have time and we have our initial velocity and the angle, we can find our initial x component of velocity, which is going to be cosine of 36 times 110, which plugging into the calculator, 110 times cosine of 36 is 88.99 meters per second. Okay, so we have our initial velocity, we have our time, and we know that our acceleration is 0. So using the first equation, it seems that that is going to be the best one to use. Delta x, which is the total displacement traveled horizontally right here, is equal to initial velocity times time plus 1/2 times acceleration times time squared. And because acceleration is 0, that entire piece of the equation becomes 0. So all we have to do is plug in delta x equals to the initial x component, which is 88.99, times the total time that our ball or a projectile is in the air, which is 13.2 seconds. And now we can plug that into our equation simply. And we get 1,174.7 meters. Okay, the last question wants us to determine the velocity of the projectile 4 seconds after firing. So this requires us to use a lot of our vector knowledge. So remember that this velocity is asking for is the total velocity. So the together of the components x and y, not just one of them. So in order to find the total velocity, we need to find the x and y components. So we need our v final x and our v final y. And we have our time, which is going to be 4 seconds. We know the acceleration in both the x and y component, and we know our initial velocity. So we can use the last row in our equation. It says that v final velocity is equal to the initial velocity, which is going to be in the x case 110 times cosine of 36 plus acceleration times time. And remember that in the x direction, there is no accelerations at all. So that component of the equation becomes 0. So plus 0. And the component that I'm talking about, in case you weren't quite clear, is this component where there is acceleration. And for our y component, we know that we're starting off with 110 times sine of 36, plus our acceleration in the y direction, which is g, negative 9.8, times the time, which is given to us as 4 seconds. So putting in the calculator for both of them, our x direction, 110 times cosine of 36, is equal to 88.99 meters per second. And in our y direction, 110 times sine of 36 plus negative 9.8 times 4 is going to give us 25.46 meters per second. Okay, now that we have our x and y direction, it's going to look something like this, x and y. We're trying to find the total velocity, and that means we need to do trigonometry, which is using Pythagorean theorem to find the total component. So our total velocity, which I'm going to use as vt, is equal to square root of vx squared plus vy squared. So plugging this in, vt is going to be square root of 88.99 squared plus 25.46 squared. Now I'm going to plug this into the calculator. The square root of 88.99 squared plus 25.46 squared. And that's going to give us 92.56 meters per second. Something really important that we should also look at that's not asked in the problem is finding the angle above the horizontal in D. So we know that using trigonometric methods, that tangent of our theta above horizontal is equal to y over x. And in order to isolate theta, that's tan inverse of y over x. Since we have both our y and x components of our velocity, we can simply plug them into our calculator using this equation to get theta. So that's going to be tangent inverse of 25.46 divided by 88.99. And that's going to give us an angle of about 15.9 degrees above the horizontal. So this is going to be our last problem, which is considered a challenge problem. So a tennis player wins a match at Arthur Ashe Stadium and hits a ball into the stands at 30 meters per second at an angle 45 degrees above the horizontal. On its way down, the ball is caught by a spectator 10 meters above the point where the ball was hit. Calculate the time it takes the tennis ball to reach the spectator and calculate what the magnitude and direction are of the ball's velocity at impact. So the first thing is to dissect this image. Using this image, we can make our own graph. We can take starting from here and here as our x-axis where the height is 0. And going from this point up, this is going to be our y-axis. As we can see, this is going to be our delta y of 10 meters, and this is our theta. So, using what we know, we can make a KUK chart. So our known variables are the v initial, which is 30 meters per second, our delta y, which is 10 meters, our initial theta, which is 45 degrees above the horizontal, and we also know that it's on Earth, so the vertical gravity is negative 9.8 meters per second squared. So what we don't know is the total time and also the final velocity at impact and the theta final. So those are the three variables we need to find. So something I wanted for you guys to take a look at is you might think that we can use the same method in order to find time, in which we took right here as zero velocity, the peak of the projectile, and use that to find the total time the ball was in the air. The reason we actually cannot do this is because the ball isn't completing its projectile. If it completed its projectile, it would land all the way here. But the reason it doesn't complete it is because of the force the woman exerts right here, which stops the ball. That is why we can't use the information here in which our v at the peak of the projectile is 0. Instead, we have to use our given information in the equation in which delta y equals to v initial y times t plus 1/2 a in the y component times t squared. So to do this, we can plug in our numbers, which is going to be 10 meters for our delta y times our v initial, which is 30 times sine 45, plus 1/2 negative 9.8 times t squared. And sorry, I forgot the t here. Okay, so now in order to solve this, we're going to have to do a quadratic equation. We're going to isolate our we can't isolate our variables. We're going to move everything over so that one side is 0, which is going to be 1/2 times negative 9.8 times t squared plus 30 times sine 45 t minus 10. And that's going to give us 0. Okay, so further simplifying our equation by multiplying out the numbers, we get our equation negative 4.9 t squared plus 21.213 t minus 10. And using our quadratic formula, we can find what t is. So plugging them in, we get our b, which is 21.213, so negative 21.213 plus or minus square root of 21.213 squared minus 4 times negative 4.9 times negative 10. And this is all under square root. Divided by 2a, which is 2 times negative 4.9. And putting this into the calculator, it's going to give us two possible answers. So solving the quadratic equation gives us two possible answers for our time, 0.54 seconds or 3.79 seconds. So in order to know which one it is, this tells us the time in which our projectile is at 10 meters. We know it's at 10 meters around both here and here. So these could be our two possible points in which our projectile's at 10 meters. And the reason that we're going to choose the longer time is because the 10 meters we're talking about is farther out in its trajectory than the first one. So it makes sense that the first one here is 0.54 seconds and here is 3.79. So that is going to be the time it takes until it is caught by the spectator. So solving the quadratic equation gives us two possible answers for our time, 0.54 seconds or 3.79 seconds. So in order to know which one it is, this tells us the time in which our projectile is at 10 meters. We know it's at 10 meters around both here and here. So these could be our two possible points in which our projectile's at 10 meters. And the reason that we're going to choose the longer time is because the 10 meters we're talking about is farther out in its trajectory than the first one. So it makes sense that the first one here is 0.54 seconds, and here is 3.79. So that is going to be the time it takes until it is caught by the spectator. Okay, part B is asking us what the magnitude and direction of the ball's velocity is at impact. So the good thing is we know the time it takes for the ball to reach the spectator, which is 3.79 seconds. And we have our initial velocity and angle. So all we have to do is look at our x and y components and figure out the addition of them. So a good visual is that the final velocity just before it hits the woman's hand to come to a stop is going to look something like this with a negative y component, because after we reach our zero velocity here, we have negative acceleration and a constant x component. And this is going to be the angle we're looking for, which is going to signify our direction. So since we have our time and our initial velocity, we can simply use the bottom equations where we find v final x and v final y. So v final x is going to be our initial velocity, which is 30 times cosine of 45. And since our acceleration in the x component is 0, we can forget about this as it cancels out to 0. And v final in the y direction is going to be 30 sine 45 minus, because our acceleration is negative, times the time, 3.79. Okay, so plating these down here, I'm going to write it down here. We're going to plug these into our calculator. So 30 cosine of 45 is 21.213 meters per second. And since sine 45 is equal to cosine 45, we just plug in 21.213 minus 9.8 times 3.79. And that's going to give us negative 15.93 meters per second. And in order to find the final velocity, we have to do the Pythagorean theorem, which is going to be square root of 21.213 squared plus negative 15.93 squared. And that's going to give us, putting it in the calculator, 21.213 squared plus negative 15.93 squared. And that's going to give us 26.53 meters per second as our final velocity. Now, in order to figure out our angle, I'm going to show you the visual representation of our triangle, which is going to be our y and our x right here. So this is going to be opposite over adjacent, so we know that tangent of our theta is opposite, which is y over x. And in order to isolate theta, we can do tan inverse of y over x. So now, plugging our velocities that we found right here into this equation, we get tan inverse of negative 15.93 divided by 21.213. And that gives us an angle of negative 36.9 degrees. Thank you so much for watching, and I hope this video helped. Below, I've linked some more practice problems that can challenge you in different ways. And in our next video, we will cover how to read kinematic graphs in 2 dimensions.